Apologies, everyone. I am here. Sorry about the delay. Let me get my camera back to where it was. Sorry, just had a phone call run a bit late. Let me clear that notepad file. That's just for today's daily activity, which we'll talk about when the time comes. Sorry again for being delayed today. Just some notes. So, homework 4 is due tonight. Homework 5 was released yesterday. It is due on Friday. And as a reminder, max 1 day late. It will not be accepted 2 days late because of the end of the term. The exam is Saturday. So we'll pick up from there. One last thing I forgot to check. Let me do that real quick. Is I believe yes, there is a quiz. There is a quiz that will be released tomorrow, and that will be the last quiz. So, quiz tomorrow, last one. At that point, you'll have your quiz grade. Are there any questions? There was a quiz, of course, due last night, which I mentioned in class yesterday. Are there any questions about the announcements today? Sorry again for the delay. Also, I just realized you can kind of see my computer screen in the mirror, but oh well. I screen share anyway. Yeah, there will be. Okay, so I will do the GOI class on Monday. I'll post an announcement when that will be. It probably won't be 1 to 3 because I've actually already scheduled a meeting at that time. So it'll probably be later just because there's a faculty meeting noon to 1, and then I scheduled another meeting with one of my advisees at 1. So I need to figure out when that will be, and I'll post an announcement on Piazza. But I'll go ahead and go through the GUI material, just understanding that obviously that won't be required for class. Um, but with that, to that end, and actually I need to delete a slide here because that slide is not accurate. To that end, last time, are you adjusting quiz grades? So again, I am going to throw one quiz out. That is to say, everyone's lowest score gets dropped. There is one question that I still need to fix. There is one question I didn't like that I'm going to give everyone full credit for. I haven't done that yet just because I've been kind of swamped with everything else. I should be able to do that this afternoon. My top priority right now is getting WebCat up for homework 5, and then that's my second one. I lie. The second one is writing the exam, but I will probably get that done today. Apologies for the delay. It's just 1 point on one exam, and I will apply that, and then again, your lowest exam score is thrown out. So, and that's already thrown out automatically by the grade book. So you can see on the grade book, your lowest score gets crossed out. Um, there's no curving on the quizzes, and I did not curve the first exam. Um, so whether or not I curve the final exam just depends on how difficult it ends up being. Which again, it's always impossible to tell ahead of time. Am I? I don't need my headset. Sorry, I have the right microphone on. Sorry, I was on a meeting that ran late, which is about actually um, the fall, which discussions are still ongoing. I don't have any information for the fall, by the way. Don't ask. I have none. That's actually why I'm in the meetings, is to try to tell people what information we need because we don't have any yet. It's a weird meeting to ask questions. Anyway, to that end, as a quick reminder, last time we talked about linked lists, and that was actually a recursive data structure. So by a recursive data structure, here is what I mean, and my camera has indeed been knocked over by a cat, as is tradition here at the Professor McBurney Twitch stream. Cameras being knocked over by cats is as American as apple pie, and not doing anything about the ongoing COVID crisis. Anyway, get the whiteboard camera lined up. Hang on. Yep. So last time we talked about linked lists and how they were a recursive data structure. And what I mean by that is if I have a linked list, let me erase this. If I have a linked list, a useful way to think of the linked list is recursively. By that I mean, this node is the head of this linked list. Right? This node is the head of this linked list. But also, you could say that this node functions as the head of this linked list. And this node functions as the head of this linked list. And so on. I have 5 colors, so you're getting those 5 colors here. And the idea is each of these lists contains, really you can think of the nodes not as individual nodes, sorry I just had to clear some marks off that, not as just individual nodes, but really the start of their own linked list. So for example, if I wanted to get, say, the sum of the integers in this linked list, I could get this value plus the sum of the rest of the linked list. How do I do that? This value plus the sum of the rest of the list. This value plus etc. So naturally this lends itself to recursion, because every structure is effectively self-referencing. It is a node referencing a node. And we can treat each node like it's the first element of a list. Now, not the overall list. This is the only head of the overall list. But we can think of each node as like a head node. So that's what we mean by recursion. And the key distinction that we're drawing today is instead of just doing lists, we can now use this same node idea to do trees. So, for example, let me, real quick, I'm fixing my Stream Deck stand so I can actually see everything. There we go. So, again, the idea of a linked list, they keep things in order. Arrays use fixed blocks of memory, which is efficient for accessing in intermediate addresses. By that I mean addresses that are neither the beginning nor the end of the list. And the linked list, which uses a series of inter-referencing nodes. So we talked about this last time. We could make our nodes generic. And by this, you know, you've seen this same thing with a linked list. You can make your node generic. By that I mean, this could be a list node of integer, or a list node of string, or a list node of Pez dispenser, or coordinate, whatever you want. An array list, it's just an array of that thing. In a linked list, it's a head node that is used to directly or indirectly reference every other node. So with the goals for this unit, we want to stick with this idea of recursive data structures, but now we want to think of it in terms of more complex structures, namely trees. And we're going to start today with trees and binary search trees. So I did change it up a bit. Can you put a primitive data type in there? No, you have to use a wrapper class. So instead of int, you use integer. instead of car, you use capital C character. Instead of lowercase d double, you use capital D double. That's so you have to use the wrapper class there. So today we're going to focus on trees and binary search trees. So this allows us to create kind of more flexible structures, albeit there may be some trade-offs there, but it allows us to create more flexible structures that are more easily able to change or reflect a particular set of needs. So the idea of a tree is we want a collection of elements that are combined in some composite, that is, it combines multiple elements, hierarchical, which we'll see what that means when we start graphing, and graph-like data structure. Now, to that end, here's what we mean by that. I can just give a quick illustration. This is a tree. The idea of a tree is it's a hierarchical structure. There is one root, and everything is descending from that root. So think of this similar to Java classes themselves. At the top, everything inherits objects, and then we may have additional hierarchies below it. Now, to this end, one weird thing about computer science is that in computer science, trees go down from the root, not up from the root. And you may think that this is strange, but it's easy to remember the fact that computer scientists never go outside, and so none of us knew what actual trees looked like when we came up with this idea. So computer science trees grow down from the top. So what is a tree? A tree is a series of nodes, but the difference between a tree node and a linked list node is as follows. Oops, wrong scene. There we go. A linked list node, which I'm going to draw in black, simply contains a value and a next pointer. And maybe, optionally, it has a previous pointer. Optionally. I got some black dry erase stuff on the green markers. Doesn't look right. There we go. But the idea is there is not really a hierarchy, it's just an order. There's previous and there's next. With a tree node, we think of this as a node containing a value, and rather than just one next node, there can be 2 or 3 or 4 or as many as you want next nodes. And optionally, you can reference the parent. But we're in a linked list. By the way, a linked list is a tree, as we'll show later. In a linked list, there's only one next pointer. With the tree, there can be multiple, and we call this the parents, the ancestors. That is anything that is up, or the predecessors, as you often also see, and then the things below are children. So it's similar to human. You would think, the things that preceded me are my ancestors. The things that will follow me will be my children, grandchildren, etc. Of course, there's the not exact translation because, of course, humans don't reproduce asexually. But if they did, this would apply. This would be helpful. Exactly, like class and subclass. So, with a tree structure, let's start throwing out some vocabulary here. First, each element hold data. This data may be unique, it may be not. But the key is every node has one parent. There's only one node that has 0 parents. The only node with no parents is the root. And a tree can only have one root. From there, each node can have 0 or more children. So every node has at most one parent, one direct parent, I should say. It can have 0 or more children, as many children as it wants. A leaf node is a node without children. So you can see in this illustration here, for example, these nodes at the bottom with no children are leaves. This node over here is also a leaf. There's the root node. This is the node from which all other nodes descend. It is the only node without a parent. So for instance, the object class has no parent. It is the thing from which all other things spring. So you could think of this, for example, like the first microorganism, maybe. But whatever it is the thing with no parents. So these nodes are the same as a linked list. Effectively, yes, they hold a piece of data, and they have children. And most of them have parents, although one won't in any given tree. And in fact, when we implement this, you'll see that it is implemented largely the same from a linked list. It is a linked data structure. So you can implement trees with arrays, and we'll talk about that later. Can internal nodes have more than one parent? No, they cannot. No node, 0 nodes at all in a tree can have more than one parent. If a node has more than one parent, it is not a tree. You can have graphs where nodes have more than one parent, but that graph would not be a tree. That graph would be some other data structure. Can we have a tree of trees? Yes, you're looking at it right here. This is a tree of trees, and we'll talk about what we mean by that in a second. But all trees are trees of trees. So the root node is the node from which all others spring. It has no parent. An internal node is a node that has children. That is any node that's non-terminal. The root node is an internal node. Very important. The root node is an internal node. And then edges are used to link parent nodes with their children. Siblings cannot link with each other. They can only link with their parent and their children. The height of the tree is the longest path from the root to a leaf. So as you can see in this tree, there's multiple paths from the root to any of the leaves. So there's 1, 2, 3. There's 1, 2, 3, 4. And there's 1, 2, 3. So the height of this is 1, 2, 3, 4, the longest path. This is height 4, this tree. Are there any questions about this vocabulary so far? I just want to make sure that we understand that before we proceed. By the way, I'm weak. I switched back to caffeine. One day. That's as long as I went. Alright, so from here, again, we have roots. The root is an interior node. Don't forget that. Each node can have 1 or more, or 0 or more children. The leaf nodes have no children. This is a tree with a height 3. Understand that not all of the branches have to have height 3. Only the longest branch has to have height 3. So trees can be useful in a lot of cases. Family trees, again, this is a little bit different. Because with family trees, of course, technically humans, do reproduce with other humans. So people have 2 parents, not 1. So it's not the cleanest translation. But parse trees are useful. This is often how your computer parses syntax, is through a tree-like structure. File systems. You can see things like, let's say your folder look like C, CS216, CS120, my mail, and each of these subfolders are within another folder. In fact, this is more or less how your files are organized, into a series of folders and files. The files are leaves, the folders are interior nodes, and the root typically is C. At least on a Windows machine, which admittedly, I am biased by Windows. So why are we talking about trees now? It's useful for looking at recursive data structures as well as recursive algorithms. So let's start let's take one step back and real quick, just to understand the rule. I'm sponsored. Oh yeah, yeah. Are trees just lists that are easier to search? I don't want to say they're easier to search. Ease implies a human ease, and that may not be the case. In theory, they could be more efficient to search, but not necessarily either. Searching in a tree could, depending on how the tree is organized, still be linear time. So trees are just lists that allow for multiple descendants. For example, a linked list is a tree. A linked list is a tree. Decision tree classifiers, what that means for a decision tree classifier is basically just a series of nested if statements, if-else statements. And I can, at the end of class, if you ask that again, I'll spend more time going into it, but I don't want to spend lecture time on it. So let's take this linked list, for example. 5, 7, 9, 10. This is a linked list with the head node. But I could also say this is a tree. The idea is I could structurally make this the same by making it, just drawing it differently and thinking of it differently. So the head is my root. The descendant of 5 is 7. The descendant of 7 is 9. The descendant of 9 is 10. Matches up the same way. The difference is, if this were a tree, I could also have some other branch, like 3 over here, and another branch here, like 8, and 2 branches down here, 1 and 4, and this would be a tree. Or I realize someone who's kind of cockeyed, standing like this. Anyway, point being, the tree has more features, but a list is a tree in this example. Trees do have broad applications in machine learning, yes. Not just in decision classifiers. Like neural networks often are built in tree-like structures, although more accurately they're graphs than trees. Typically neural networks don't form trees, they form just generic graphs. Anyway. Okay. So, any questions about the syntax or the vocabulary of trees before we move on? All right. So the next one we have is we're going to narrow our definition. We're going to split all trees into 2 kinds: binary trees and general trees. And if you're familiar with binary search trees, I am not talking about that right now. I will later. A binary tree is just a tree where each node has exactly 0 to 2 children. So 0, 1, or 2 children. No leaf can have more than 2. Or excuse me, no node can have more than 2 children. And because there's no more than 2, we can denote a definition of left and right. So, for example, this 5, 7, 3, 10, 6. This is a binary tree. This is also a binary tree. If I say 8, this is a binary tree. Up here is my root. I'm going to underline in red my leaves. This is a leaf, this is a leaf, and this is a leaf. My interior nodes, I'm going to underline in purple. Interior, 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 interior. And the idea is, because there's 2 children, I can naturally break them into left and right. Yes, so a linked list is a tree, but you can think of it like a unary tree. Whereas a binary tree can have at most 2 children, a linked list can have at most 1. And the idea is every node is a left, 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 or a right, right, right. So we can go from the root, and we can find any node by either going left or going right. Those are our choices. But because this is a binary tree, I can have 0 children, or 1 children, or 2 children. I cannot have more than 3. If I were to say 7 here, this is no longer a binary tree because I've added a middle child. Now, when we're talking about a binary tree, we don't really care broadly about why something is left or right. We just define the children as left and right because that's an easy distinction when we have 2. Now, we can add meaning to left and right, which we will do later in the class, but in a binary tree, left and right don't have any meaningful meaning. Are there any questions about that so far? So now, there's something to note about these tree structures, which we haven't yet talked about. And it is that a tree, and let me make sure the full slide's on there. If all nodes have one child except leaf, is it a binary tree? Yes, it is. So a linked list, a singly linked list would be a binary tree. Technically, a doubly linked list would be as well, because the child is just pointing to its parent. So yeah, that would be a binary tree. But you can understand the value of thinking recursively here, because, as I've said, this structure is a tree. Right? That much is trivial. But also, this structure is a tree. And this structure is a tree. And this structure is a tree. And even just this node is a tree. The idea is every node is the root of its own subtree. So all trees are trees of trees. And if you think about it in that term, it makes it actually quite easy to start thinking recursively. A tree with no nodes, it's simply that the root, in a case of an empty tree, the root would be null. This would be an empty tree. Obviously, this tree on the left isn't empty. So this is a pretty simple application of what we talked about with linked lists. The idea that a linked list is empty when the head node is null. The tree is empty when the root node is null. Make sense? But a root doesn't have a parent. That is correct. That's fine. There's one node that doesn't have a parent. And by the way, we could have parent pointers. I could add to this that this node also has a parent pointer. That doesn't make it not a tree. Right? The trees can have back referencing. It's just understand how many children there are. But does each tree need a root? Yes, every tree has to have a root. Otherwise, it can't start. You can't have a tree without a root, because the tree has to start somewhere. If an object is circular, it's not a tree. Yeah, if you don't have a root, you can't have a tree. The tree has to start somewhere. Okay. So now, going back to our general description of a tree, but a tree within a tree is okay. I mean, all trees, all nodes are the root of their own subtree. Like, I circled a bunch of groups of nodes to say those are subtrees. So every node you can think of as the root of its own subtree, but the overall tree only has a single root. So for example, and actually this is going to get back to our next slide, so in a general tree, we could define the tree recursively as a root that points to several subtrees. How does it point to those subtrees? By pointing to the root node of those subtrees. So, going back to the whiteboard, this is the root of this is the root of the subtree 3, 10, 6. This is not the root of the overall tree, but this is the root of that subtree. I forgive me, I don't understand that post. Pointing, not thinking of it necessarily as a parent. Forgive me, I don't understand if you're asking something. But the idea here is 7 is also the root of this subtree. 8 is the root of this subtree. 9 is the root of this subtree. But it's not the root of the overall tree. Could we have objects of the tree class instead of ints inside the data field? Okay, I think you guys are really, really overthinking this. Could we have objects of the tree class? I mean, yes, you can put a linked list. You can have a linked list of linked lists. You can have an array list of array lists. You can have an array list of array lists of array lists of array lists of array lists if you want. The question is, what is useful? I have never tried to do a tree of trees. I'm sure you could do that if you wanted. You can make an array list of any data type you want, including array lists. And the same holds true for any generic data type. The question is, what is useful? And in my mind, what is useful here is to think of the tree as a tree containing a root node and several subtrees. But this tree itself could contain integers or strings or Pez dispensers or, coordinates. And yes, it could also include binary search trees. But if you have a binary search tree of binary search trees, it's just, why do you need that structure? Maybe there's a situation where you absolutely need that structure. That's incredibly valuable. I can't think of it, and I'm not going to spend lecture time trying to come up with one. Like, again, you can make the tree of any data type you want under the sun. But focus on the tree before you try to get too deep into the weeds of, like, it's a tree of array lists of trees of array lists of linked lists of trees of array lists. Like, you could do what I just said, but the question isn't can you, the question is why. And I just want to make sure that that's clear. So try to understand the basics. Like, we're trying to walk right now. I know some of you are ready for Formula 1, but let's just try to walk. All right. So from there, again, you can think of it recursively as a root connecting to several subtrees. From there, if I wanted to define a binary tree node, I could simply define it as some piece of data. And again, I put E here, but this could be T or anything else. We have some piece of data and a left and a right. This is a binary node. Now, if you wanted more, you could have more. You could put as many as you want. If there is no left or right child, then the left would be equal to null, and or the right would be equal to null. So this is the same way we express the linked list, only instead of next, we would have left and right. So from there, a binary tree is the class. It's a separate class from the node. Just like when we did lists, which, just like when we did lists, give me 1 second. Just like when we did list, we had a node class that was separate from the list itself. This is the node class, and yeah, it's an inner class, but it's still a separate class. And this are the fields of the list. So list contains a head node, and in this case a tail node, the same way a binary tree will contain a binary tree node, but they are different things. The tree we define separately from the node. And we can define methods that act at the tree level, and we can define methods that act at the node level separately. For example, the size of the root of this tree, starting from here, the size of this is the number of elements in the tree. 1, 2, 3, 4, 5, 6, 7. But I can also get the size of a node. For example, if I got the size of this node, 3, well, it has 2 children plus itself. So the size of this node is 3 because it's the size of its subtree. The size of the tree, not any one node, but the tree, is the size of the tree from the root node. So again, this blue tree, this subtree is size 3. That is part of the size of the overall tree. Does that make sense? So we can think of things from the tree perspective as well as from the node perspective. So with a binary tree, again, we're specifically defining the binary tree as a tree like any other, except with a limit, an upper limit, is the size of 7, 2, or 3. Hang on, let's go back to the whiteboard. The size of 7 is 3. Because 7 has one child and one grandchild and itself. So the size of 7 is 3. So it's not just the size of the node and its immediate children, the same way that the size of 5 is 7. The size from the node 5 is 7 because it has 3 children to the left, or 3 descendants to the left, I should say, 3 descendants to the right, plus itself, so 7. So now, we think of the top of the tree as the root, and the tree class is going to contain that root. From there, the tree class will contain that reference and methods that apply to the entire tree. The node class can then be recursively defined. It's recursively defined because a node contains nodes. A node contains a pointer to a left node and a right node. And now those may be null. If in case of a leaf, left and right will both be null. But the point is, it has those pointers. It contains some piece of data, and it has methods that can be defined recursively as referencing the node. So some tree methods that are worth knowing. Size, height, and find. We can define these methods not just at the level of the tree, but also at the level of the node. So, for example, and I'd still need to upload these later. But for example, if I were to define a binary tree, and we can do that now. New class binary tree T. I can make this of any data type generically, T. This is going to contain a binary tree node, T. Which, by the way, these are uploaded with the daily activity today. So you can download those there. Root. From there, of course, I need to create this class, so I'm going to go ahead and create it. The binary tree node T contains some data type T data. It contains a binary tree node T left and a binary tree node T right. So T is a placeholder. T can be any data type under the sun at all. It can be literally anything. So from there, I can then say, all right, so let's have, and I'm going to write real quick just public static void main string args. I would say something like binary tree node integer tree equals new binary tree node integer. I could then say tree.root equals new binary tree node integer, let's say 5. Sorry, this shouldn't be a tree node. Forgive me. Binary tree, I meant. Sorry. It's a typo there. And this, I need to create the constructor. Is just going to say t_val data equals val, left equals null, right equals null. So this is the same as the constructor I made for linked list. And then from there, I can add to the tree doing something like root dot, and let me, I'm going to make these, for now, for the sake of simplicity, I'm going to make these public. In the daily activity, they're private, but there are setter methods. But just for the sake of time, I'm making these public. Root dot left, or excuse me, tree dot root dot left equals new binary tree node integer 3. And I can do the same with right, with 7. So I could construct a tree in this type of way, and you could have done the same with linked lists. And by the way, this is not a great way to actually build them. You want to define a generic add method, and we'll talk about that later. But with a binary tree, we just can do whatever we want with this in terms of adding things into the tree in whatever order we want. From there, if I want to get the size of my binary tree, well, the first thing to take into account is the tree empty? So I can define a method like public boolean is empty, and the tree is empty when what is true? What, based on the fields that I have, or in this case field I have, when will the tree be empty? When root equals null. Right, so return root equals null. If root is null, this is true. If root is not null, this is false. Okay? From there, public int size. Now, there's a couple of ways to do this. But this is, in my mind, the easiest way. First, we say, okay, if is empty, then obviously we return 0. If the tree is empty, then obviously the tree can't have any elements. Else, I'm going to do something. I'm going to instead outsource the problem, and rather than try to solve it in the binary tree, I can try to solve it in the return in the node class, root.size. Now, I, of course, have to define this function, but I can say, hey, give me the size of the root. And this is where we want to take a step back and do some diagramming. How do we determine the size of a node? Well, the way we determine the size of a node is we first remember that our node is the root of its own subtree. And so, let's consider how we can generically define this. I'm going to draw this really big. Let's say our diagram looked like this. 5, 7, 3, 10. Now, the size of my tree, clearly here, is 4, right? But how can I get this recursively? Well, let's consider first, what is our base case? Well, what I need to think of is if I have a node, if I'm looking at a node as the root of its own subtree, what node, what kind of node, could I immediately say axiomatically the size of this subtree is blank? What would be true about that node for me to be able to, without doing any more work, say the size is some number? For instance, what is the size of the subtree of this node? Because remember, this has a left and a right, it's just that they're null. The same is true of every leaf. Remember, we have these nulls here. We don't draw them because, dry erase markers aren't free. But so, this is my base case. A leaf. If I call size on a leaf, that's my base case. How do I determine if the size is, or how do I determine if the node has no children? If left and right equal null. So let's for now define that. Let's define our base case inside of this recursive function size to be the following. If left equals null and right equals null, return 1. The size is 1, not 0. The size is 1, not 0, because, going back to the whiteboard, this is a node. The only way the size is 0 is if root is null. And if the root is null, we couldn't be calling this function anyway, because there would be no root to call it on. Remember, in this case, I am in the class tree node. If the root were null, we would never call on a node the size function. We would just at the tree level say it's 0, moving on. So we never call null.size because we can't. This cannot be null. You can't do null.size because null is not a tree node. So it's always at least 1. It can't be 0 because otherwise the node wouldn't exist to begin with. So from there, now I can go one step further. Okay, so this is our base case. Our non-base case is the size of a given node. Pick any node, this one. The size of this node is equal to the size of the left subtree. So left dot size plus the size of the right subtree. So right dot size plus 1 for itself. And so, the way I could write this, I could write it a number of different ways. The way I'm going to choose to write this is the following. I'm going to say int size equals 1, counting the node itself. If left is not equal to null, I have to put in this safety check so I don't get a null pointer exception. Pardon me, a null pointer exception. Lost breath there in the middle of the sentence. Size plus equals left dot size. Notice I'm not doing else if. If I did else if, it would be wrong. I'm just doing if right not equal to null. Size plus equals right dot size. I'm not doing else if because it's possible that there's both a left and a right child. If it were either or, yeah, sure, else if is fine. But it's not either or. It can have both. And then return size. And that is my size function. And to check if this works, I've created a tree with 3 nodes. Let's go ahead and test it. System.out.println tree.size. And you'll see that I get the size 3. And again, the idea is the tree only decides, hey, is it empty? If it is empty, return 0. If it's not empty, I'm going to let the node class handle this. And this is a recursive definition. Notice I'm recursing on the size function on the left and the right. This is my base case. This is my recursive step. Are there any questions about this size function? Any questions at all? So again, remember, there's two separate functions at play here. The tree size function and the node size function. And be aware of how they interact. From there, we can define the height function. The height function, going back to the whiteboard, is the number of nodes from the root to the leaf, the largest path. For example, I have 3 paths here. I can go 5 to the left. That's one path. I can go 5 to the right. And then if I try to go to the right, it's null. Or I can go 5 to the right and to the left. So the height is the largest distance. So in this case, the height is 1, 2, 3. Notice it's not 2. It's 3. Why is the height 3? Because, why is it not 2? Because it's not the number of moves, it's the number of nodes on the longest path. And understand that the reason we call this 3 instead of 2 is because, consider these 2 trees. I have this tree, which is a single node. Null and null. This has a height of 1. And then I have, and this is my root. And then I have a second tree where root equals null, and this has a height of 0. So if the tree is empty, its height is 0. If it has exactly 1 node, it's a height of 1. And then from there, you can calculate height recursively. So let's do the same thing. First, public int height if is empty, return 0. Else, return root.height. And then from there, I can define my function recursively. Again, my base case is the same. If it's a leaf node, the height is 1. Now it's a bit trickier though, because I can't just use the same for size. The same for size doesn't apply. For example, I'm going to write in red the height of each subtree. So at the bottom, let's start with our leaves. This is a height of 1, and this is a height of 1. What is the height of this tree? 3. Anyone? What is the height of this tree? Starting with 3. 2, right? Because 1, 2. So now, what is the height of this tree? 5. It's 3, but it's not this plus this. It is, for example, if instead this tree also had another child. And for the sake, I'm just going to draw it in here. 12. Let me change this. So this tree would have a height of 1. This tree would have a height of 2. Now what height does this tree have? It has a height of 3. And if I were to fill in another node on the left, this tree now has a height of 2. And my question is now, if the left tree has a height of 2 and the right tree has a height of 3, what is the height of 5? Is it 5? 2 plus 3? What is the height of it? Not 3, because I have a child that is 1, 2, 3, 4 away. It's 4. The height is whatever the larger subtree is. So this, I have a subtree of size 2, or a height 2, excuse me. Subtree of height 2 and a subtree of height 3. It is the larger of these two plus 1. It is the larger of the left and the right plus 1. And so, what I can do is I can say the following. First, I'm going to define int left height, left 8, and I'm just abbreviating it to h, and right height. And I'm going to initialize these two values both to 0. And then, if left is not equal to null, left height equals, and it's just going to simply be left dot height. Just recurse and get the height of the left tree. And same with right height. If right is not equal to null, then right h equals right dot height. And then from there, I'm not going to return the sum of these two values. I'm going to return 1 plus math.max of these two values. That is, whichever value is larger. And yeah, you could replace this with an if statement if you wanted. If left greater than right, return 1 plus left, and blah, blah, blah. This is another way to do it. So this is the same idea. So now, just to illustrate that this works, I'm going to add another node to my binary tree. Let's add another node, and this one is going to be tree root.right.right equals new binary node 2. And let's add even another. Tree node.right.right.left equals 5. Or let's do 4 for now. So now, if you draw this, you would notice that the largest path is 1, 2, 3, and 4. So my height should be 4. Let's make sure that works. Whereas my size is the number of nodes I've added, which is 5. So this should be 5. This should be 4. And that is indeed what I get. Any questions? All right. Last one. Last function we're going to do. Then we're going to take our break, and we're going to come back and talk about binary search trees. The last function is find. Now, I want to be clear. Some of you, I know, already know about how to search a binary search tree. This is not a binary search tree. It's a binary tree. Very, very different. How am I going to check if a value is in the tree? You can think of this like contains. So rather, public boolean contains t value. How am I going to check if a tree contains that value? Well, I can start the same way as before. If the tree is empty, obviously the value can't be in the tree. Return false. Otherwise, I'm going to do root.contains. And now I add that recursive function. And now let's consider what we would do. If I were checking to see if a tree contains a value, what is my base case? Well, once again, not surprisingly, the base case is if left and right are null. If the left and the right are null, then there's two possibilities. Either the leaf is the value I'm looking for, or it's not. To that end, I could write this actually a little bit differently. The first thing I would check is if value dot, and it would be contains, excuse me, contains, I would need to pass in the value. I forgot about that part. T value. If data dot equals value, then I found the value. I found it. And at that point, I can just return true. Else, if it is not that, and I don't need the else if here because, remember, return, it would return immediately. It would never evaluate this. So, if the left and right are null, and the data is not the value, what should I do here? The value of the leaf node that I'm at, because I'm at a leaf node in this case, does not match what I'm looking for. What should I return? I'm looking for something. The leaf node does not contain it. Are there any children to search? No, there's no children to search, so exactly. Return false. So this is leaf node with different data. Now, I need to consider interior nodes. So this, I should be clear, this is not really a base case. Because technically we could recurse further. We just don't need to. No, I wouldn't return null. This is a Boolean function. So I would not return null. Null is an object. Booleans are not objects. I'm returning true or false. Those are my choices. So now, for interior nodes, where data does not match value, what would I do? Well, let's say I were looking for the value 12 in this tree. If I'm at the root, if I'm here, then obviously this is not equal to 12, but it's not a leaf node either. So what I'm going to do is I'm going to search for 12 in the left tree and search for 12 in the right tree. And if either the left or the right produces the value I'm looking for, it doesn't have to be in both, it only has to be in one, then I'm going to assume the value is in this tree. In this case, 12 is in the right subtree. So the way I can do this is the following. I can simply say else return, and I don't need the else here again. I can, because again, if I reach this line of code, neither of the ifs were true. Return left dot find, or left dot contains value, or right dot contains value. Now the problem I have, I can't just do this. I can't write the code this way because left may be null and right may be null. So I have to first take a step and say something like if left is not equal to null, then I could say something like if left dot contains value, return true. And this is a way to write it. A slightly more stylish way to write this would be if left is not equal to null and left dot contains value. And you don't have to worry about a null pointer exception here because of something called short circuiting. This would also work as well. Then from there, if right is not equal to null and right dot contains value, return false, or sorry, not return false, return true. And then here we just return false because we've checked the left and the right, it's not there, therefore it must be false. So this is contains. Let's go ahead and test this. So to test this, we're going to first do two searches. System.out.println tree.contains let's do 4. This should be true. And let's do tree.contains 11. This should be false. Let's go ahead and test it. And we get true and false as expected. So, I'm going to leave this code up for find. You can copy it down, or obviously you can always back reference. We're going to take a 10-minute break. We'll be back at 2:22. I will see everyone then. Go ahead and get yourself a drink, snack, whatever, and we'll be right back. All right, hello everyone. I hope you've been enjoying, by the way, the Skies of Arcadia soundtrack. It's a really good soundtrack. I love the music in that game. It is my favorite JRPG by far. It's also really hard to find. I think last time I saw it listed on eBay, Skies of Arcadia Legends for GameCube, which you want the GameCube version, it's better. Last time I saw it, I think it was listed at like 200, so it's hard to find now. But you know, there are other ways. Cough cough dolphin, cough cough emulator. Anyway, just putting that out there. It's a really good game. Anyway, so the standard format that we have been using so far for these recursive functions, or for these functions with a tree, is at the tree level, if it's null, return some fixed result, and if not, call the function on the root node. And then at the node level, base case, the node is a leaf, return some fixed value. Otherwise, recurse down the left if there is one, recurse down the right if there is one, and then return some result. This is the general format of most of our functions that we're going to be doing. So this is the standard idea of a binary tree. But now, I want to go one step further. Because so far, I mean, we have this left and right idea, but it's not really useful right now. Right now, it's just, okay, it's like a linked list, but harder. Yay! Not very helpful, right? So why would we bother with this? Well, the idea is I want to combine this idea of a tree with the ideas of binary searches. So remember, the binary search was the idea that you take an array, you look in the middle. If the middle is greater than what you're looking for, you look to the left. Sorry, from your perspective, to the left. And if the middle is less than what you're looking for, you look to the right. So to that end, how can we apply that here? Well, we can use this tree structure in order to look things up like a binary search. So first, remember that the array list, by default, uses a linear search. When you use the contains function, the array list uses a linear search. And Java does not check to see if the array is sorted, and if it is, do a binary search. Now, you could write a binary search on the array list, but the problem is every time you insert a value, you have to insert it in sorted order, or the search becomes invalid. So instead, what we're going to do is we're going to combine trees with a binary search to create a binary search tree. And a binary search tree is a binary tree that adheres to the binary search property. By that I mean, a binary tree can store anything that is comparable, but it has to be comparable. You have to have a way to say this thing is less than or greater than or equal to that other thing. How can you compare classes? You don't compare classes, you compare instances. This tree does not store classes. It stores instances of some class T. Right? 3 is not a class. 3 is an instance. How do you compare objects? Comparable. That was something we covered, I want to say, before the midterm, I think it was. You implement comparable. That is the default way. So if I were to make this a binary... Oh, did not mean to do that. What did I just... Okay. If I were to make this a binary search tree, new class, binary search tree, and then from there, I would also need a binary search tree node. It's going to look very similar, but there are some differences. So first, instead of just being T, it's T extends comparable. This is saying that T must be an instance of comparable, specifically T. And this looks weird, but it just means that whatever value, whatever class that you put into the binary search tree must be a class that implements the comparable interface. And we can do the same here. There we go. Why is it not implements? Technically, because we're talking class hierarchies, I mean, I could say implements, but the way that this works, the way this parameterization works, it doesn't accept the word implements, it only accepts extends. And yes, technically you implement comparable, you don't extend it, but just the limitation of what goes inside these brackets, you're qualifying what type of class can go in here, and it has to be a class that is a descendant of comparable, even though comparable is an interface. There's not really a great reason. It's Java, but it's just you can't put the word implements in here, so the word extends works. From there, largely this class will start the same. In fact, I can do almost every method the same, although we will get later into some distinctions. So, instead of this being a binary tree node, this is a binary search tree node. And then from there I can add into binary search tree node all of these methods. Now, I'm not implementing them for the time being, but the difference is a binary search tree, the nodes actually have to behave differently. And the way those nodes behave differently is via the binary search tree property, which specifically states all values in a left subtree, not just the left child, but every value in the entire left subtree must be less than a given node. And every node that is in a right subtree must have a greater value than that node. And this doesn't just apply to the root. This is for every node. So notice, yes, 8 is greater than 5 and 3 is greater than 5. But also 6 and 9 are greater than 5 and 1 and 4 are less than 5. So it applies not just to the immediate descendants, but to every descendant. And this is a pretty useful property. We'll talk about an in-order traversal tomorrow. But it should be noted that binary search trees are actually how tree set and tree map are implemented. Can two numbers be equal? So, Can you do a binary search tree in the abstract where you allow for equal values? The answer is yes, but you have to decide ahead of time, are equal values always to the left or are they always to the right? In practice, however, that proves difficult. So generally, I want to say not always. Could you envision a binary search tree with duplicates? Sure. But generally, you treat a binary search tree like a set, which is to say that you do not allow the insertion of duplicate values. You treat the binary search tree like a set. Duplicate values are not allowed. Generally. And the tree set is actually implemented with a particular implementation of a binary search tree. Now, I want to be clear, it's not a generic binary search tree. There's specific examples, like AVL trees and red-black trees that you will learn about in 2150, that are balanced. And we'll talk about how balanced is a meaningful distinction later. These trees will always be balanced, and a binary search tree by default won't be. And that has a meaning. We'll get to that a bit later. If a tree is balanced, search times are log of n, whereas an array list is n. Now, a hash set is constant time, provided you have good hashing, but it doesn't have sorting, whereas a binary search tree is by default sorted. So here is an example of a binary search tree. And let's take note. Our root is 43. So not only is 25 less than 43, but every node in this subtree is less than 43. 25, 11, 31, 28, and 39. Similarly, the right subtree, every value is greater than 43. 69, 54, 66, 71, 76, 99. But that property does not just hold true for the root. It's also true for this node 25. Everything to the left of 25, which is only 11, is less than 25. Everything to the right, 31, 28, and 39, is greater than 25. Similarly, look at 76. Its left child, less than it. Its right child, greater than it. This means 66 is an interesting position because it is a right child of 43, because it's greater than that, a left child of 69, because it's less than that, and a right child of 54, because it's greater than that. Any questions about this? That is, every node in the tree, not just the root, adheres to this property. Similarly, this is a binary search tree. This is also a binary search tree. You may not have seen this before, by the way. We didn't actually get there with the slides. So the bottom node on the right will always be greater and the left be the least. Not necessarily. Not necessarily. For example, depends on what you mean as the bottom. 7 is arguably the bottom here. And 7 is neither the greatest nor the smallest value. The farthest right value is if you start from the root and go right and only go right, you'll eventually hit 23 as the leaf. That will be the greatest value. And if you start at the root and go left and only left, you'll hit 3. That will be the smallest value. But it's not necessarily on the bottom row. See, this tree is not balanced. And we'll talk about what we mean by balanced a little bit later, but this is not a balanced tree. Counterexamples. This is not a binary search tree. 1, we have 3 child nodes. 1, 2, 3. That's not even a binary tree, so by that token, it cannot be a binary search tree. Second, the left child of 20, 21, is not less than 20, so this would not be a binary search tree. What about this? Is this a binary search tree? Again, we generally will assume in a binary search tree it is not, because we don't have 1, we don't have the binary search tree property preserved. 4 is not less than 1. 3 is not less than 2. 1 is not less than, or 2 is, sorry, 1 is less than 3. 2 is not greater than 3. But second, we also have duplicates. So this is not a binary search tree. What about these? Write in chat if you think they're both binary search trees, A and B. If only one, A or B. And if neither, say neither. So I'm expecting in chat A, B, or neither. Go. Which of these are binary search trees? We're getting some B's. That's good. You're all saying B. Even though this doesn't look like a tree, right? It doesn't really look like a tree. It almost looks more like a a linked list, right? But this is still a binary search tree because 30 is less than 34. 34 is less than 42. 42 is less than 57. This is an unbalanced binary search tree, but it is one. It is a binary search tree. Over here, the one counterexample that makes this not a binary search tree, 19 is less than 20. So therefore, 19 could not be in the right subtree of 20. So this is not a binary search tree. So B is, A is not. And this takes us to a problem. Because when we talk about finding later, we're going to talk about how in a balanced binary search tree, find is log of n. But if the tree is unbalanced, if you wanted to find the value 57, that would take n steps. Therefore, searching an unbalanced binary search tree is not log n, it is n. Just be aware of that. Is this a binary search tree? Once again, no, because this is not even a binary tree. So now, how do we do find and insert in a binary search tree? Well, let's start with the idea of find. Let's go to the whiteboard, and I want people to first just give me numbers between 1 and 20, try to make them somewhat randomly ordered. Give me numbers 1 to 20. I'll take probably 6 or 7 numbers. Let's start with 17. Actually, let me do a more. I'll do 14 as my root, and then we'll add 17, and then 19, and then I saw a 16, and then I saw a 7, and then do 3, and let's do 10. This is a valid binary search tree. Does anyone see any problems with it? I just want to make sure I don't have any problems with them. This is correct. Now let's talk about how we do find. Let's say I wanted to find the value 10. The way I would find the value 10 is first I would say, okay, let me look at the root. Is the root empty? Is the root null? No. So obviously we're going to have to search. But the advantage of a binary search tree is, unlike a binary tree where I had to search both the left and the right, with a binary search tree, I don't need to search both the left and the right. I only need to search one side. For example, if I'm finding 10, well, if 10 is in this tree, based on our binary search tree property, would 10 be in the left subtree of 14 or the right subtree? Left or right? Would be in the left, because 10 is less than 14. So because 10 is less than 14, I search to the left. So I have gone first, I started at the root, and I recurse down to the left. From there, 7 to 10. right? Because 10 is greater than 7, so I would search to the right. And look, I found 10, so I return true, which returns true, which returns true. So this is still recursive. Now, let's say I were trying to find the value, let's go with 18. And actually, let me do find 18, not in red, but in blue. Let's do find 18. If I were to find 18, I would start once again at the root. And if 18 were in this tree, because again, I can't see the whole tree, I can only see this root. This value is not 18, so would 18 be in the left or the right subtree? The right, right? Because 18 is greater than 14. So I recurse on the right, and now I see 17, and I say, okay, would 18 be in the left or the right subtree? Would 18 be in the left or right subtree of this node? Right again, exactly, because 18 is greater than 17. So I recurse again. Now, once again, this is not 18. Would 18 be in the left or the right subtree of this node? Would 18 be in the left or right subtree? It would be in the left, right? Or correct, I should say, it would be in the left, correct? Yes. But the problem is this is null. And because this is null, that means that by following the path I should follow to find 18, I didn't find it. And so, because it should be in the left, but there is no left, this returns false, which returns false, which returns false. A similar structure, but the difference is where in the binary tree we search both the left and the right. In the binary search tree, we did not search both the left and the right. We only searched the side where the value could be contained. So when we build our tree, we have to make sure it adheres to this property. Are there any questions about find? And obviously, if we were searching for, say, 17, let's do purple. 17 would be to the right of 14. Oh, look, we found it, so we return true. So we return true. You don't have to search the whole way down. But if the tree is balanced, then, because of the structure, if it's balanced results in find being O log n. But if it is not balanced, because again, it's possible that we have a linked list that is sorted, in which case that could actually be a binary search tree, then an unbalanced is going to be O of n. And we'll define more specifically what we mean by balanced later. For now, just assume you can eyeball it, and we'll give a more formal definition later on. Are there any questions so far about find before we move on to insert? All right. So from there, discussing insert. Since 18 was not in our tree, let's go ahead and let's insert 18. So I'm going to do insert 18. Now, the way I insert is I start up at the top and I say, all right, I need to look left or right. Well, which direction do I look? If I'm going to put 18 into this tree, would I put it in the left subtree or the right subtree? Remember, it's a binary search tree. It has to be in one side. It would be the right subtree. I have to put 18 in the right because 18 is greater than 14. So I recurse to the right, and I call this node .insert18. Now from there, 17, should I go to the left or the right? Well, 18 is greater than 17, so I recurse once again to the right. And then from there, I hit 19 and I say, okay, 18, if it's in this tree, would be to the left, so I'm going to insert it to the left, except I can't recurse to the left, because remember, there's this null here. So in order for me to continue, now I just replace this null. I just create a new node 18, and I say this node dot left is 18. So when I'm inserting, I start at the root, I work my way down until I reach a null, and I replace that null with the node. Let's now try to do insert 1. If I were to insert 1, 1 is less than 14, recurse to the left. 1 is less than 7, recurse to the left. 1 is less than 3, but because there's a null node, I can't recurse, so I make the left child of 3 the node containing 1. Now, let's insert 2. And now when I insert 2, same pattern as before, 2 is less than 14, 2 is less than 7, 2 is less than 3, which I can now go down, 2 is greater than 1, and so I insert 2 down here. And by the way, this tree is actually now unbalanced. There's a mathematical way to say this particular insert made the tree unbalanced. We'll talk about what we mean by that in a second. Last one I'll do, let's say I were to insert 7. Let's say insert 16. If I were to try to insert 16, 16 is greater than 14, go to the right. 16 is less than 17, go to the left. Oh wait, this value is 16? Okay, then I'm just going to stop there. I'm not going to create any new nodes. So are there any questions about find and insert in a binary search tree? And that would be, again, insert 16. Any questions about find or insert in a binary search tree? All right. So from there, just go through these slides here. So again, if the tree is balanced, it's O of log n. That is, the worst case is actually the height. Because the worst case number of nodes you would check for find or insert is the height of the tree. If the tree is balanced, the height is proportional to the log of the number of nodes. If the tree is unbalanced, then the height could be as much as n. And so you can actually do, if you think of this would be a binary search tree, if this were your sorted array, you would do the binary search on this array exactly the same way you would do a find on the binary search tree. Because notice, 5, 5, 11, 11, 12, 12, 14, 14, 15, 15, 18, 18, so on. So the process you would use for a binary search on this sorted array at the bottom is exactly the same as what you would get for the binary search tree up here. Which that's pretty cool. Now this is called a complete tree. A complete binary tree is one where up to this level, every possible space is filled in. That is, every node except the nodes at the bottom level have both a left and a right child. And every node at the bottom, obviously, is a leaf. This is not the same as balanced. So when I say balanced, I want to clarify what I mean. A balanced tree And I don't need this anymore either. A balanced tree is one where for every, not just the root, every node, the height, I spelled height wrong already, the height of the left is within 1 of the height of the right. Is within 1. So it's not exact. They don't have to be equal. They just have to be within 1 of each other. So, obviously, 5, 3, 4, 1, 7, 6, 10. Obviously, this binary search tree is balanced. It's also complete. If I erase 10, this tree is still balanced. It's not complete anymore, but it's balanced. But interestingly, this tree is also balanced. Even though there's more elements to the left than the right, the height of the left is 2, the height of the right is 1, are within 1 of each other. So this is balanced. And in fact, now my question to you is, given that definition, is this balanced? Yes or no? Pick a side. We're at war. I want you having to type yes or no. Yes, it is balanced. No, it is unbalanced. Yes or no? I did get someone saying not balanced. All right, remember that definition. If the height of the left and right are within 1, so let's work this out. Let's start with the leaves. The leaves are easy. The leaves are always balanced. So yay, we're done with that part. Now let's start with bottom up. Is 1 balanced? Well, the left height is 0, the right height is 1. They're within 1 of each other, so that's balanced. Now let's try 3. The height of the left is 2, the height of the right is 1. They're within 1. This is balanced. 7, the height of the left is 0, the height of the right is 1. Balanced. Now, 5, the height of the left is 3, the height of the right is 2. This is balanced. So this is a balanced tree. But if I were to add a node as a child of 2, let's say 1.5, now this is no longer balanced, because this node won't be balanced. Because the height of the right tree will be 2, the height of the left tree will be 1. Now, there are ways to insert into a tree where you reshape things such that you always make sure the tree is balanced. And examples of that you will see later, not in 2110, are AVL trees and red-black trees. Actually, you know what? I have colored dry erase markers. Let's do this the right way. There we go. Red-black trees. All right. You will see these in 2150, and they are self-balancing trees. That is, the insert property will ensure that the tree maintains balance. By default, though, the binary search trees we are working with in this class will not self-balance. And that's okay for the sake of this class. We're just getting started. We're getting our feet wet. So, just to quickly look through the rest of the slides, let me hit my slides button. Nope, didn't mean to do that. Ignore that. To that end, we have I do actually have, yeah, so I cast sometimes, and that's actually a league I cast for. Anyway, to that end, here's pseudocode for Find. I'm not giving you actual code, and the reason for that is in some semesters and possibly next term, one of the homework assignments is implementing that. I chose to do the linked list rather than the binary search tree. A, because I wanted to change up. B, because I knew I wouldn't cover binary search trees on Monday, and I wanted to give a realistic timeline for the homework. I didn't want to release the homework on Tuesday that would be due on Friday. So again, how do we find an insert? Just simply, how would you insert 33 into the following? 33 is greater than 30, less than 40. You insert to the left. Now, deleting is a bit trickier. Deleting is trickier. It's a lot trickier, actually. Deleting. You cannot just remove a node. You can't just remove a node. So, for example, if I were to, from this tree, want to delete 3, I can't just remove the node because 8.left has to point to something. So what you can replace it with is the successor. And the successor node is the farthest left node in the right subtree. That is the next largest value. So then that's because if you look in the right subtree, all the values are greater than 3. And the smallest value in the right subtree is the leftmost value. So I find 4. 4 is the successor. It's the farthest left child in the right subtree, and I simply replace 4 with 3. Given that, how would I find the successor of 38? The successor of 38 is we go to the right, and we keep going left until we can't go left no more. And we can't go left no more at 41, and so we would replace 38 to delete 38. We would replace it with 41. And then, in that case, 43 would become the left child of 55. So to illustrate that, let's go to the whiteboard. And there's a number of possibilities here. Let me not use green. Green is bad. Green doesn't show up well. Let's say I have 7, I have 5, I have 10, I have 12, I have, we do 11, actually, let me change this number from 10 to 11. Let me make this number 8, and this number 9, and even then, let's make this 10. And 4. So if I were to remove, if I needed to delete a node, depending on different factors about the node, I would have to do different things. For example, if the node has 0 children, let's say I wanted to remove 4, well, that's easy. I find the parent node of 4, and I say this node.left is null, and that will delete it. That's easy enough. I could just delete a node with no children. But if instead I were deleting a node that had 1 child, well, that's also fairly easy. If I wanted to delete 5, well, 7 still needs a left child, and it still needs to connect to 4. All I would say, okay, if I need to delete this node, I'm just going to say 7.left is whatever child. And it doesn't matter if this child is the left or right. For example, if 5 only had 1 child that was a right child, I would still just say the parent, in this case, because 5 is a left child, the parent.left is the child. And then that would delete that node, which garbage collection would remove it. So if it only has 1 child, fairly easy to do. By the way, I'm not intentionally not showing code for this, because the code for this is actually a bit tricky. But the tricky one is if I need to delete a node with 2 children. Or 2 children. For example, let's say I needed to delete the node 7. if I needed to delete the node 7, I have to find the successor, which is the leftmost child of the right subtree. You can also find the predecessor. That is the next most value that is smaller than 7. So the value in the rightmost value in the left subtree. But let's do the leftmost value in the right subtree. Well, for 7, that would be, go to the right child, and then keep going left till we can't go to the left no more, 8. Now, this is a bit tricky, because 8 also has a right child. The first thing I'm going to do is I'm going to replace this value with whatever value is here. So I'm going to make this 8. And then, rather than delete this node, I'm actually going to delete this one. And, based on what I said earlier, we actually know how to delete this node. You delete this node by simply connecting the parent to the one child, which will always, in this case, be a right child, because if this node had a left child, we would have kept going. We wouldn't have swapped 8 with that. So this is a bit tricky. Deleting from a binary search tree is a lot harder than inserting. Suffice it to say, you're not going to have to implement that, but you should know the process of how it's done. And that's covered in the reading as well as here on the slides, which are uploaded. So there's 2 different versions. There is the rightmost of the left subtree will be a predecessor. It's the largest number smaller than the value being deleted. That's the predecessor. And the successor is the smallest number larger than the number being deleted. So there you go. You can see the idea. So with that, today, this is the in-class activity, and I'm going to be wrapping up lecture from there. What you are going to do is you are going to download the 2 things on Colab, so I will download them now. It's binary tree, even though this should technically be binary search tree. But binary tree node. And then we're also going to download binary tree. So we're going to download both of these. And then from there, we're just going to put these into our program over here. So let me delete these 2 files. And I'm simply going to click and drag these into Eclipse. And what we want you to do on this assignment. Give me a second. I have too many windows open. I'm losing track of everything. What we want you to do on this assignment is we want you to insert the values into, that is, build a binary search tree as though we inserted values in this order. So we would start, since the first value is 6, we would start by writing in main, and we're going to do this in binary tree node main. Don't worry about all the code up here. These are mostly just getters and setters. What we're going to do is we're going to start by defining a root, except the value that we're inserting first is not 1, it's 6. So, I'm going to insert 6. From there, the next value I'm going to insert is going to be a new binary tree node for 4, correct? Now, will 4 go to the left of the root, or will it go to the right of the root? Will 4 go to the left of the... It'll go to the left. So I could say root dot left equals. And there we go. And then from there, you would just keep going. So the next value is 3. 3 would go to the left of 4, because it would go to the left of the root and then the left of 4. So I would say root.left.left equals new binary search tree 3. And from there, all you need to do is insert all these values in order. So first 6, then 4, 3, 5, 8, 9, 1, 2. That's the daily activity. Are there any questions about this? And by the way, at the end you can call the toString method. This should print. And we'll talk about why it prints this way in the future. Yeah, you don't need to write an add method. Just for now, hard code it. We're not having you write an insert method. Though you're welcome to practice writing an insert method. Originally, the homework for this class often is to implement a binary search tree, so you would write an insert method, but we're not doing that here. You're just hard coding it. This is just to make sure you understand the binary search tree property, as well as get some practice with directly referencing pointers, left and right. And then that is it for today. So with that, I will see everyone tomorrow. Remember, homework 4 is due tonight. Homework 5 is due Friday. It is out. I will get the WebCat tests up for homework 5 tonight. They're not up yet, but they will be. With that, just to answer an earlier question, a decision tree is effectively, you can think of it like a tree. The idea is, it's more like a flowchart is what you would call a decision tree. You reach a point, if some condition is true, you go left, otherwise you go right. That's a decision tree. And that is, a decision tree is trying to translate an AI model into a human-readable model. That is, a human can follow along with how the decision is made. What we're finding is that the best AI models are ones that humans don't easily understand. They're actually very unstructured. So the Go robot, the robot that beats the best human players at Go, that is actually model-less learning. It's not, the model that exists is not designed to be human interpretable. If you want to look into that, you can. It's the difference between modeled learning and model-less learning. But with that, I'm going to wrap up. Thank you all for watching, and I will see you tomorrow. Take care.